to the session again. Okay. So, in the previous session we were discussing about the Nyquist plot and we were observing its example, and we had seen in the previous session how with the help of Nyquist plot or Nyquist contour we can draw our plot, and by the formula n equal to p minus z we can determine the stability of the closed loop system. Okay. So, in today's session we will discuss about the Nyquist plot example, and we will begin with the introduction to the Bode plot. Okay. So, in today's session we will discuss first example, then we will go for Bode plot introduction. So, in the previous session we were discussing the Nyquist plot of this transfer function, if you remember, and we have done the 3 step map of S1, map of S2, map of S3, right, and S4 was remaining. So, this was S1, this was S2 and this was S3. Okay. So, S1 we had done the polar plot like this. This was our S1 plot, if you remember from the previous session we had done this calculation. This is the map S1. The same way map S2 was one point at the origin, map S3 was inverse polar plot. So, I would like to make its inverse polar plot like this. It should be mirror image of map S1. It will start from omega equal to minus infinity and terminate at omega equal to 0, and here my map S1 start from omega equal to 0 and terminate at omega equal to infinity. So, this step we have done. Now, our remaining step was map S4. So, in the map S4 we need to observe it is starting from minus 90 and terminating at plus 90. Okay. So, this is the step S4, we are not including S4 here. Okay. So, this step we have done already, this will be our step S4. In the step S4 what I will do, in the GS I will replace S by limit r tends to 0 r exponential of j theta. So, here this radius is r, okay. This radius is r which is going to 0. I already explained why, because we need to take a very small area, because we are not including here pole at the origin, that is 1 over s. Okay. So, in this case I need to put in the GS. So, GS is given by k over s multiplied by s plus 1 multiplied by s plus 2. So, here my s is going to 0, s is again going to 0, it means s is very small value. So, as compared to 2, s is very small, so we can neglect, it is 0. The same way as compared to 1, this s is very small, so I can assume it is very small value near to 0. In that case what I will get, so here I am getting k over 2s, right. Now, I need to replace s by this function. So, here I can assume 2 as a constant, so it would be k over limit r tends to 0, s is given by r exponential of j theta. So, here r is tending to 0, this will make k by 0 exponential of minus j theta. Okay. So, k by 0 will give us infinity. So, I can say my expression is equal to infinity exponential of minus j theta. Okay. What is theta? Theta you need to observe from the previous graph, it is varying from minus 90 to plus 90. Okay. So, I can write theta is varying from minus 90 to plus 90. Okay. So, here I can write it is equivalent to minus pi by 2 to plus pi by 2. I need to replace here infinity exponential of minus j theta is from minus pi by 2 to plus pi by 2, or if we solve it, it is from minus exponential minus and plus, sorry, minus minus will become plus j pi by 2 to infinity exponential of minus j pi by 2. right. It means this curve will move from plus 90 plus pi by 2 to minus pi by 2. It means plus 90 to minus 90. It means we have to move in clockwise direction to map S4. So, how I can map S4? In the map S4, I need to start from plus 90 and I need to terminate at minus 90. Okay. So, how much phase I need to cover? First, I will go from plus 90 to 0, first quadrant, then 0 to minus 90, second quadrant, and total phase shift is around 180. So, this is my map S4. Okay. So, I will include this map in the previous plot. So, I will start from plus 90, I will start moving like this and terminating at minus 90 and I will complete this curve like this. So, this is the Nyquist plot for this case. Okay. So, now we would like to see whether it is stable or not. So, what I will do? I would like to check whether this curve is enclosing minus 1 or not. Okay. So, for that purpose I must know this value x. Okay. What is this distance x on the real axis? Okay. So, what I need to do? How we can determine this value x? What is this intercept value? So, for that purpose we will determine here omega p c. Okay. So, we will determine here omega p c. Okay. Okay, let me. So, with the help of omega p c we will get value of x. Okay. So, how we can say we will determine omega p c? In that case the phase is going to the minus 180 line. So, if 180 phase is our 180, this is 0, this is 90, this is 180 and it is touching the this line at 180. I need to calculate the magnitude. So, what is the alternate way? I can calculate from the transfer function. So, here our transfer function is given as g s equal to k over s, s plus 1, s plus 2. I can replace s by j omega. Okay. Then we need to separate out real and imaginary value. So, we will get here g s equal to k upon s, s plus 1, s plus 2, replace s by j omega, I will get k over j omega plus 1, j omega plus 2. I need to separate out real and imaginary value, k over j omega, this will become minus omega square j omega and plus 3 j omega plus 2, this will come. If I further solve it this will come k over minus j omega cube, or you can say minus 3 omega square j square, because this will multiplied by this minus 3 omega square, then plus j omega would be multiplied by, you can see the remaining term, minus omega square plus 2. Okay. So, here there is no complex term present in the numerator. So, I can directly separate out the real and imaginary term from the denominator. If any complex term present in the numerator, then I have to make the complex conjugate and then I need to separate out real and imaginary value. But here real and imaginary is present only at the denominator. So, I can separate out from the denominator only. So, here my imaginary part is 0. You can see if we want to know the x intercept, my imaginary value would be 0, then we will get here real value. This concept we had seen in the polar plot, or if you solve the numerical polar plot, then you would be very clear about it. Okay. So, I will put this imaginary term equal to 0 minus omega square, you can say imaginary term equal to 0. So, minus omega square plus 2 equal to 0. From here omega is plus minus you can say under root 2, this is omega p c. Okay. And now, I will put this omega p c in the real value of this term, then I will get the value of x. Okay. So, here my this real value is k over minus 3 omega square we would like to know this value at omega equal to omega p c. So, if I put here, this will become k over 3 multiplied by 2 with minus sign, and this is minus k over 6. Okay. So, this term is coming, x value is minus k over 6. So, here x is minus k over 6. Okay. Now, for stability, I am assuming this plot is passing through minus 1. Whenever this x is equal to minus 1, you can say if x is equal to minus 1, so you can say system is marginally stable. If you know stability concept from polar plot. So, I can say minus k by 6 is equal to minus 1, or you can say k is equal to 6, right. So, here we can explain stability on the basis of k. If k is less than 6, this is one case. If k is greater than 6, if k is less than 6, it means whole plot will not encircle minus 1, and value of n equal to p minus z, n will be 0. There is no pole in the right half plane, we can say p is 0, then z will be 0, my system is stable. If we are saying k is greater than 6, then minus 1 will lie here. Okay. So, now this minus 1 is encirclement by this curve one time in clockwise and second time in clockwise. So, n is equal to minus 2, or from formula n equal to p minus z, we can say minus 2 equal to p, p is 0. So, I can say 0 minus z, and z is equal to 2, it means 2 poles lying in the right half plane, and my system is unstable. Okay. So, in this way we are determining the stability using Nyquist plot. So, one more example is here, this is for type 3 and order 4. Okay. Same step, step S1 map polar plot. If you do the step S2, you will get one dot at the origin, same step that we have done. To map S3, its inverse polar plot, it will go like this. Now, how to map S4? Okay. So, that is why I had taken this example. For S4, this will be k over s cube, and we need to replace s by r exponential of j theta, where limit r is tending to 0. So, here if s is very small, then we can neglect s from here, and we will get only s cube, 10 is very high, this will multiplied by 10. So, this will be k over s cube if I assume 10 in constant k. Okay. So, I can replace this k by r cube exponential of 3 j theta with right, and limit r tending to 0. Again this will gives you k by 0, that is infinity magnitude with exponential of minus 3 j theta. Okay. What is value of theta? Theta is varying from, if you see the Nyquist contour, theta was varying from minus 90 to plus 90 to map S4. Okay. S4 के लिए we had seen plot is from minus 90 to plus 90, it means minus 3 j theta is from minus pi by 2 to plus pi by 2. If you solve it, it is from plus 3 pi by 2 to minus 3 pi by 2, or you can say it is from plus 270 to minus 270. So, how we can do this plot? So, this is my plus 270, sorry, this is my plus 270, 0, 90 and 180, then plus 270. In the same way, this line is minus 270, right. So, how many time I need to move? We need to move in clockwise. So, first I will start from plus 270, this is my starting point. I will go for first quadrant, okay, it is 90, then 180, then 270, right. After moving this plus 270 times in clockwise, I am reaching 0, then minus 90, then minus 180, then I will terminate to the minus 270. So, we need to move around 2 times in this case, and we will get this Nyquist plot. Okay. So, this is the case. So, total distance we covered around 540 degree between plus 270 to minus 270, and the same concept you need to see whether it is enclosing minus 1 or not, then you can determine the stability. So, this is about the Nyquist plot. Now, we will discuss basics of the Bode plot. Again, just like the Nyquist, Bode plot is again a frequency domain analysis, right. So, here this Bode plot basically we use in all the application, whether we are going for a control system, whether we are going for analog electronics design or frequency analysis design, or you can say small signal parameter S parameter design. So, in that case we have to take the help of Bode plot. So, basically Bode plot consists of two plot, one is magnitude and phase plot. Okay. So, the magnitude plot is obtained by putting S equal to j omega, that is sinusoidal transfer function, okay, and this plot will be in between the mod of g j omega h omega in dB versus log 10 of omega. It means in the x axis we will make log of 10 omega, this is my frequency in log, and here in the y axis I will take magnitude, but in dB. Okay. So, this is my Bode plot. It will consist of two, one is magnitude and phase. The phase plot how we can obtain, again we need to put S equal to j omega to obtain the sinusoidal transfer function, right, and we need to calculate its mod, and we need to calculate its angle g j omega h omega, and we need to plot with respect to log base of 10 omega. Okay. So, how we can do this we will see later. Okay. So, first we would like to see the application of this Bode plot in determination of stability of system. Okay. Again we are observing here open loop transfer function, and with the help of that we would like to estimate the stability of closed loop system. So, here we would like to see for stability gain margin and phase margin with respect to the Bode plot. Okay. So, here this is my magnitude plot, you can see this blue line. Here I am plotting with respect to magnitude, and here in the x axis I am plotting frequency log 10 of omega. Then second is my phase plot, this is my phase plot, okay, where I am plotting the various angle with respect to frequency log of 10 omega, and this is my magnitude plot. Okay. So, here how to calculate the gain margin, this is my magnitude plot. How we will draw this plot we will discuss later. First we would like to see this stability concept with respect to this Bode plot. Okay. So, first I need to calculate the mod of we need to calculate the sinusoidal transfer function by putting S equal to j omega in GSHS, and then we need to calculate omega, this mod value at omega p c, and this will give us value of x. You know this concept from the previous case. Okay. So, gain margin given by 1 over x. So, if by discussing this thing in terms of dB, so I will take logarithm both the sides. So, my gain margin will be given by log of 1 is 0 in the divide, it is x in the denominator, I can write minus of x in dB. Okay. So, if we get the value of x from this plot, then we can calculate the gain margin. Okay. So, how we can calculate this? So, for that purpose I need to calculate omega p c. So, omega p c is the frequency where my phase plot is touching minus 180 line. This phase plot is touching minus 180 line at this point. I had taken the reference line minus 180. Okay. So, at this frequency what is my magnitude? So, it is intersecting here. Okay. So, if I see my magnitude here, it is minus 20 dB. Okay. So, here my value of x is minus 20, I will put in this formula. So, this is coming plus 20 dB. It means this is my value of x plus 20 dB. So, this is the margin available in gain in the system. Okay. So, here gain margin is coming positive. In the same way, if I want to calculate the phase margin, I will focus on omega g c, that is gain cross over frequency. We had seen where our mod is equal to 1. It means our magnitude will equal to 1 at omega g c. So, here we are observing all value in dB. So, I will see log of 1 is 0. So, I need to check where my magnitude is cutting 0 line at that point my frequency would be omega g c. And if I observe my phase plot at that frequency, this is my phase, this point is here around minus 140. Okay. So, phase margin given by P m equal to 180 plus phi, where phi is this phase at omega equal to omega g c. So, phase at omega equal to omega g c is minus 140 phi. Now, phase margin would be given by 40 plus. Okay. It means my phase margin is coming positive. So, what you can see, this is the phase phi is available to us the range of 40. Okay. So, here one more thing you can see, here omega g c is less than omega p c. This is my omega p c location, this is omega p c, this is omega g c, and this is the condition that we declare in the polar plot for stability, right. So, this is the stable system Bode plot, where gain margin is positive and phase margin is positive, and we can say our system is stable. Okay. Later we discuss how to make this magnitude plot and phase plot. In the same way, if we look for marginally stable system, where this magnitude plot cutting at 0 here and this phase plot cutting minus 180 at this point. So, first I will calculate gain margin, again I will calculate my mod at omega equal to omega p c. This is my omega p c, where my phase plot cutting minus 180, and I would like to see at this frequency what is the magnitude. This magnitude is coming here 0, right. So, here what we can say, gain margin is 0 minus x, x value is coming here 0. So, here 0 minus 0 will gives you 0 dB. So, here my gain margin is 0. Okay. Now, what about the phase margin calculation? In the phase margin, it is given by P m equal to 180 plus phi, where phi is angle of g omega at omega equal to omega g c. Okay. So, here this is my omega g c, where my magnitude cutting the 0 line, and at this point what is my phase? My phase is coming at this point is minus 180. It means at this frequency my phi is minus 180, phase margin 180 minus 180 gives me 0. It means when gain margin, phase margin both are 0, then we will get here marginally stable system. Okay. In the same way, we will come for third case, unstable system. So, in the unstable system, what we are getting here, my omega g c is higher than omega p c. This concept we had seen. So, first we will like to see our magnitude plot, phase plot. For gain margin, I need to calculate omega p c, my phase plot cutting minus 180 at this point. Now, I would like to see what is magnitude here. It is around plus 30 dB. So, this distance from 0 to plus 30 is the value of x. So, for gain margin 0 minus x, 0 minus plus 30, and this is giving me minus 30 dB. In the same way, for phase margin calculation, we can make phase margin equal to 180 plus phi, where phi is again my angle at omega equal to omega g c. So, this is my omega g c, where my magnitude crossing the 0 line, and at this frequency what is my phase? This phase is coming around minus 260. Okay. So, here my phi is minus 260. So, phase margin is equal to 180 minus 260, again it is around minus 180. It means both gain margin, phase margin is negative. It means my system is unstable, and you can see this condition here, omega g c is coming here, omega p c is coming here. So, it satisfies this condition, and this is the condition of instability. Okay. So, here with the help of Bode plot, we can see this stability condition. Now, we would like to see the construction of Bode plot, how we can do this magnitude and phase plot. So, first we will discuss how to do magnitude plot, then we will go for phase plot. Okay. So, here first step is we need to determine the gain constant or constant c. Okay. So, we need to convert our transfer function in time constant form. It means in 1 plus s t form. Okay. So, suppose we are getting a g s equal to 1 over 2 plus s. So, I will convert this in 1 plus s t form. I will take 2 common 1 plus s by 2. So, this is my standard format. I need to convert, then I will determine the value of k. This is my step 1, okay, where k will gives you the DC gain. Okay. So, suppose Gs is equal to k only, then Gg omega equal to k, and I would like to plot my magnitude in dB. So, Gg omega dB equal to 20 log base k, right. This C is equal to 20 log base k. So, here we will see the various value of k. If k is equal to 1, C equal to 20 log base k, it is 20 log 1, it is equal to 0 dB. It means in the magnitude plot I will make here a 0 dB line. This is my value at k equal to 1. If I make k equal to 10, it is 20 log base 10 k, 20 log 10, this is equal to 20 dB. It means for k equal to 10, I will make this straight line. For k equal to 0.1, 20 log k, it is 20 log 0.1 and minus 20 dB. It means for this case, I will plot this line, it is for k equal to 0.1. Okay. In the same way, we will like to see the certain poles and 0 at the origin. Okay. So, here Gs is given by s raised to power plus minus n. If n equal to plus 1, it means 1 0 at the origin. If n equal to minus 1, 1 over s, it means 1 pole at the origin, and n equal to minus 2, it means 2 pole at the origin. So, what is happening here in case of magnitude 20 log base 10 of this omega, if I replace s by j omega, this will come, then mod of Gg omega equal to mod of omega raised to power plus minus n. If I take log, this will come, then plus minus n factor will come here from log property, this will come, and this will give us a basic you can say a slope, right. Whenever n is equal to plus 1, it means 1 0 is here, this will give us a slope of 20 dB. If n equal to minus 1, this will give us a slope of minus 20 dB. If n equal to plus 3, this will give us a slope of plus 60 dB. Okay. So, how this will happen, we will see in the next lecture. So, thank you for today.